and everybody's ready to get started on a nice afternoon session. So my name is Betsy Roberts. I'm the director of the Center of Malting Excellence at Barista Malt and Ingredients. And I will be introducing all the speakers, and as Max mentioned this morning, no lengthy introductions, anything. Speaker bios are available on the website if anybody wants to see any more information. So to get us started, this session is titled Breeding Progress, Building Resistance. This session will highlight several of our barley breeding programs and will provide updates on the work to build resistance against disease threats. And I guess without further ado, our first speaker is Dr. Rich Horsley, barley breeder from NDSU. Thank you.
I didn't know I was supposed to talk about disease resistance. I got a slide with a couple talks on a couple markers for net blotch and spot blotch. But thank you for the invitation, and let's see if we get this to work. There we go. What I want to talk to today, you heard a couple talks this morning on genomic selection, and I'm going to talk about, how we use it in our program. Basically, how do we use new technologies? How do we determine if we're making progress? Is it really working for us? And then, does it save us money? Ultimately, that's what it comes down to. Can you be more efficient in your breeding programs, and can you do it at a lower cost? So when I was hired a few years ago, and we had two barley breeding programs at NDSU. We had a 6-row program and a 2-row program. I was hired as the 6-row breeder. At that time, we had 3.5 million acres of barley in North Dakota, and over 90% of it was 6-rowed. There's not 3 million acres of barley in the U.S. now. Things have changed quite a bit. In 2006, we still had the two barley programs, but Jerry Frankowick retired and went to be a barley breeder in Australia, in Queensland. And one of the things that was driving his decision was there wasn't a lot of interest in 2-row. And he wasn't going to get much funding for 2-row malt barley in North Dakota, because every acre of 2-row in North Dakota was one less acre of 6-row. They wanted 6-row out of North Dakota. And at that time, when Jerry retired, they consolidated the two programs. And at that time, it was about 2/3 of the material in the program was 6-row, and about 1/3 was 2-row. And then starting around 2011 and 2012, you start hearing discussions out there about, maybe there is a place for 2-row. Maybe, there's some economic advantages there. Maybe you should start thinking more about 2-row on your program. And so we started making more crosses, and you can see now in 2015, 2016, definitely have more 2-rows in the program. We flipped about 2/3 2-row, 1/3 6-row. And then in 2018, got that phone call in December, and I was told no more 6-row. We're only going to be testing 2-row out of AMBA. So right now we're 100% 2-row and 100% spring barley. And so it's a crowded slide, but I'll try to walk you through it and try to make it less crowded. For a breeder, for a spring crop breeder, this, you would think that the summer is the busiest time of the year, but it's really not, because you're only concentrating on one thing. Put the crop in the ground, take some notes, collect the data, and then harvest. And so it really is, it's a quite easy time. Yes, the weather can be frustrating. Those diseases can cause you a lot of heartaches. But it's not really until you get right to harvest where things get extremely busy. And you're going to see there's yellow for September and yellow for March. And that's where genomic selection is applied in the program. But from when you harvest, or right even before harvest and during harvest, you've got about a 1-week decision time to decide what's going to winter nursery in New Zealand. Because we're harvesting about the middle of August, but that seed's got to be leaving to go to New Zealand about September 10th. What's going to the winter nursery in Arizona? And you got to start packaging that material up. What's going to be malted by Madison? Because it's first come, first serve. And so everybody's sending their material right after harvest, and they all want the data back quick enough to make decisions on what to advance. And then what am I going to be sending to Tom Baldwin for foliar disease testing in the greenhouse? What am I sending to Gene for dawn testing? And most importantly, what is going to be planted in that crossing block in the first week of September? So all of that's got to be done with all of that new data in about a 1-week period. After we do that, then it's kind of slow down. We're just starting to collect data once again. We're getting data sent to us on malt data. We're getting dawn data and foliar disease data. And then February comes up and we got to analyze all the data again and determine what's going into next year's yield trials. And then March becomes extremely busy because then we got to decide what gets harvested in the winter nursery and what goes into yield trials. So this is following that 10-year scheme to get a variety, but we're going to be using genomic selection in two places in the breeding program. One is, what crosses should we make? And then the second place we use genomic selection is here in the Arizona nursery. This F4s and F5s. We have about 4,000 to 4,500 rows down there. I got a picture of it. And which ones do we advance to go into our yield trials? And then the rest of the program. In case there's a question at the end, I've always get questions, will genomic selection reduce the time it takes to develop a new variety? And I would say, no, not really. It just makes you more efficient. But yes, I think it can. In our program, we have 4 levels of yield trials. Preliminary is the first year, intermediate, advanced, and variety yield trial. If you're like the corn companies and the soybean breeders, if your genomic selection is very successful, you can completely eliminate this level of testing. You can do it all on the computer, which is scary as brought up as an applied breeder, but it's very possible. So to be able to use these tools and really to make everything efficient, you need a lot of data scientists behind you. And we're very fortunate at NDSU to support our 10 breeding programs. We have what's called the NDSU Ag Data Analytics Team. It's about 12 individuals, computer scientists, computer engineers, database architects, statistician. I mean, it's a very expensive group of individuals, to say the least. But a heck of a team that's developing these tools that we can use for our breeding program. I'll kind of highlight 2 of them briefly. One's called Ex Libris, and one is called Predict Pro. So if you're in extension or in breeding, we've all developed these type of tables. We have to send these tables by March 1st to Scott every year, right? And it looks like a very simple table, but how long does it take to make that table of all of your data in Excel, right? So this is 6 years worth of agronomic data. And if this was in Excel, it would be in over 50 files, 50 separate files. And while we were still using Excel a while back, I would do this once a year, make all these tables for over 200 lines, and it would take me over 2 weeks. That's how I spent my June, is making these tables for this and for malt quality. So only once a year, we were generating fresh results. But with Ex Libris, our database with our data team, this is all 24 traits in the program. This is my variety trial. And this is data across 4 years. And we're able to generate that table in less than 3 minutes. And so you go from something. So now every day you get new data, you can generate these kind of tables and you can make decisions using the most up-to-date data. You're not using data that's 9 months old. And so this is how we're using for crossing. Just to explain this, let's ask some of the farmers out there. Anybody raise cattle or swine? So EPDs, you guys have been using EPDs to decide what crosses to make for decades. Us plant people were kind of slow. We're just getting to this now, but basically it's the same theory. We decide what crosses to make based on expected performance differentials. And so this is when I was using genomic selection. We use Jump Genomics, which no longer exists. So we're using another program now, but it's still the same. I had 278 possible parents. It generated over 38,000 crosses, but that includes reciprocals. And so it generated every single cross, even the selfs. And the selfs are important to me because I can tell, do the data look realistic, or do they make sense? Conlon should have extremely high beta glucan, Pinnacle a little bit lower, and Genesis a little bit lower, but still everything else is going to be much, much lower. So for each line, it would develop the average of 200 lines. So this would be the average of 200 lines from that cross. It says a 6.07. This is a minus 26.92. Don't worry about the negatives. Low is low. The lower, the better. And so you can see out of these 38,000 crosses, I picked about 96 that year. And this one had very low beta glucans, early heading date, high yield. And so this is what's predicted to happen. And it works. And you're going to see at the end that using this kind of information pushes your breeding program in the right direction. Wow. In the winter nursery is the other place where we use genomic selection, and I can't help but use 6 rows. I still got to look at 6 rows just for my sanity. And this is where we were going. Look at that nice semi-dwarf 6 row. It would stand anywhere. We can still bring them back. And so in this nursery, each one of these rows is about 8 feet long, and it comes from a single head. And so we have about 4,000 to 4,500 of these. And each one of these rows, we have the genetic fingerprint of it. So using that data from the genetics of each and every row, we can predict what's the beta glucan, what's the yield going to be, what's the heading date, based on predictive modeling. The other thing, the old way of doing things before genomic selection, it was just a beauty contest. You'd go through the file and go, well, that's a 1 to 5. That one's pretty, that gets a 1. That one's a little taller, a little ragged, maybe that's a 2. And that's what you did. You brought home the 1,200 prettiest rows. I mean, that was technology. And then you had stuff like this. These were the 2 rows. You can see what I think of 2 rows sometimes. And those are all 5s. They're just all lodged. You would never bring that kind of material home. This is Yuma. It's only 3 hours east of here. Here's the top of the car. So you can see how tall the barley gets down there. If it stands in Yuma, it'll stand almost anywhere. And this is what the old field book used to look like. It was just the row, the label, and just the phenotype score on the 1 to 5. And I would rate it 2 to 3 times in March. And you bring back the 1,200 prettiest rows. So this is what the field book looks like now. There's no way you're going to read it, and that's okay. But you can see now what's in here, that same information, but now we have all the genotype data. I have the haplotype or the genetic fingerprint for dormancy for 3 different loci. I have the genetic fingerprint for spot blotch resistance, net blotch resistance, and then I have the predicted beta glucan, the predicted DP divided by protein, because DP is so correlated with protein, just divide it by protein and pick the highest value. And you just treat these like real numbers. I mean, treat it like it really is beta glucan. And then you get something like this. Wow, it's got really low beta glucan. It doesn't matter if everything is great over here. If it lodges, there's no reason to bring it back. The farmer's not going to grow it. And then you're going to bring back something like this. It had low beta glucan, early heading date, high DP, some resistance to spot blotch, net blotch, a little bit of dormancy. And so that's the kind of material you're bringing home. And so you saw this formula this morning or something similar to it. This is what we're all taught in plant breeding classes, genetic gain. How quickly are you making gains? And if you work for a private company, your whole life is based on that. If you don't have high genetic gain, they're not going to keep you in the company. So selection intensity, what's your percentage you're selecting, the heritability, and the standard deviation of the phenotype. That's one way to measure genetic gain. Are you being successful in your program? This is a formula that takes into consideration genomic selection, because now you're worried about accuracy. What is the correlation between the predicted value of a line and the actual value of that line? So you predict the beta glucan to be 40. Is the actual beta glucan, when you get the data in that range, that's your accuracy. You want that number to be high, and then your standard deviation, the additive variance, and then the length of your cycle. And that's another thing genomic selection does. You get to use parents probably 2 years sooner than you would have. So this is a really complicated slide, but just to kind of walk you through it, ignore the title. The x-axis is the year. You see there's a vertical red line here. So before 2017, I did not use genomic selection for beta glucan. Okay, I started using beta-glucan in 2017. Bob Rugerman used to do my genotyping for me. And then what we have these green bars. This is the percent of lines that have beta-glucan numerically lower than Genesis. Percent of lines lower than Genesis. Not a very high bar. Genesis is pretty high in beta-glucan, but still, we're going the right direction. The yellow bars is the percent of material 50% lower in beta-glucan than Genesis, and the red is synergy, because I started using synergy as a check in 2018. So let's go here, pre-genomic selection. I used to bring back 1,200 lines, the 1,200 prettiest lines from Arizona. And of those 1,200, only about a third of them had beta-glucan lower than Genesis. That means that the 1,200 I brought back, only 400 even had a chance. I wasted money testing 800 plots, or 800 entries. That's a lot of money, you'll see in the last slide. Since genomic selection, almost 100% of the lines, so it's over 95% of the lines, have beta-glucan lower than Genesis. Over 60% of the lines now have 50% lower beta-glucan than Genesis, and 40% have lower beta-glucan than Genesis, or than synergy. So that's definitely going in the right direction. The other thing, 2024, that's a new SNP array I'm using. We'll see if I have time to talk about that. But here I used to test 1,200 lines. I no longer have to test 1,200 lines. I only bring back 500 to 600 lines from Arizona. I test a lot less material, and almost all of that material has lower beta-glucan than Genesis. That's a heck of a lot of savings there by not testing material that's going to fail in the end. I can't figure out the right direction here. And the same thing for heading date. This SNP array wasn't designed for heading date, but it was pushing heading date earlier than Genesis and earlier than Conlin. This is really where we want to be, earlier than Conlin with high yield. So the original array was 600 SNPs, and it was designed specifically for beta-glucan. I designed it for my program for beta-glucan, for net blotch and spot blotch. And it was really being successful. And so, I work with 24 different traits every single year. Can I get this genomic selection for all of the traits, or at least half of the traits? And so I developed prediction models for every single one of these traits. Well, it was a couple steps. First, I needed to design a new SNP array, and it needed to be somewhere between 3,000 and 4,000 of these markers or SNPs, because the cost point was right. And I wanted to see, could I develop it for these traits? The other thing I needed to do is figure how many markers do you really need for genomic selection of beta-glucan, for heading date, for yield, for dawn. And so what this is using all of the data for beta-glucan. Beta-glucan is the poster child for genomic selection. So your accuracy was about 0.74, but if you used 18,000 markers and just picked the best 1,000, you lost very little accuracy. You're down to about 0.72. And then if you get down to about 100 markers, you're down to 0.68. It doesn't take a lot of markers to select for a trait. So now you can build this SNP array for 24 traits and still keep under that 4,000 SNPs. And this is the other thing you got to decide. That helps you decide how many markers do I have to use. This is again from Jump Genomics at the time. PredictPro does the same thing. How many markers? And you can see even with 50 markers, it's ranking the lines from low to high very accurately. And so that was extremely encouraging. So I built a SNP array. It's 3,600 markers, and this is just a partial list of the traits. And it goes from 0.72 accuracy. So heading date, we have 50 SNPs on there. Net blotch, there's 50. See, yield is 200. Height has never worked for me on this, but so that's the current array we're using. It's about 3,600 SNPs, and all those lines in Arizona get genotyped. So how does this save money? So this is pre-genomic selection, testing 1,200 entries, and the design was 2 locations, 2 reps, so that's 4,800 plots. And so how much does it cost to grow that plot, to harvest that plot, collect the data, and then hopefully malt the grain from that plot? Is it $25 per plot? I think it's more than 25. 50, maybe if all you're doing is collecting the data, not malting it. But if you're malting that line, it's not very, if you're gonna malt the grain from that plot and you actually had to pay for the quality testing, it's gonna cost you more than $100 for that plot and the grain harvested from that plot. So we'll stick at 50. We can look at that. So that's $240,000 just to phenotype, collect data from those plots. I'm down to 600 plots. I changed my experimental design. It's 4 locations, 10% checks. We're down to 2,600 plots. It cost $132,000. Just cutting the number of lines saves a hell of a lot of money. And as a breeder, it's really weird because the first question breeders will ask each other, how many plots do you have? Well, I've got 10,000. Well, I've got 11. Everybody wants more and more and more. And it feels so wrong to go backwards. I tell you, it just doesn't seem right. Used to have 25,000 head rows, down to about 12,000 head rows. That makes me feel good because head rows are a lot of work. So you're saving a lot of money just by putting out fewer plots. But there's a cost to genotype those lines. So 4,000 lines, it cost me about $18 to genotype per line. So there's a fixed cost of $72,000. So by genomic selection, if I'm at $50 a plot, I'm saving $60,000 a year. I'm testing fewer lines. I'm putting better lines into the program, and it's just working. And if you're at $100 a plot, if you're going to malt those lines, and you can actually predict what the beta glucan and the extract and the DP and the alpha and the wort protein are going to be, you're approaching $200,000 in savings if you can get that model to work. So that's the power of genomic selection. Is at the end, you're going to get more lines in your breeding program at the very end that have the traits that the maltsters want, that the brewers want, that the farmers want. And it's actually going to cost less money. And if you feel weird about going with smaller numbers of lines to test, that's okay. It's normal. It's weird, but it's normal. So this is the last slide. I wasn't sure I was going to show this. I was at a conference a couple of years ago. And if you've been a malt barley breeder, all your friends that develop soybean and wheat and all these other crops, they release varieties all the time. If you're a Midwest malt barley breeder, if you can get a new variety every 6 to 10 years, that's okay. So I thought at that time, ChatGPT. I was sitting at Prairie Grains in Grand Forks. So what's easier, develop a new malting barley variety or find a group of beer drinking unicorns in a bar? I should have seen, or whiskey drinking now too. And well, in the 1980s and 90s when I started, the unicorns might have been easier. If you think it's hard to release a variety now, in the 1980s, only 3 6-row varieties were approved in the Midwest or enter the AMBA list of recommended varieties. In the 1990s, only 3 varieties got added to that list. Nothing got added to that list. 2000s would come up later, and all these new varieties are on the list. Oh, this is easy, but you got to get the brewers to use it. So I don't know. That was my frustrations one day. And so ChatGPT can be kind of fun, you know. So I'm going to finish up there. And, you know, all of this work wouldn't be possible without the funding from our sponsors, you know, American Malting Barley Association, Raw Malting, the money we got from them, all went to the genotyping. The North Dakota Barley Council have been a tremendous supporter for all these years. The SCAB initiative from the USDA is our biggest supporter. Most of our money, a lot of our money comes from them. The USDA ARS, we have some cooperative agreements to support our data analytics team. And of course, the experiment station at NDSU. So I'll go ahead and finish there. I'll dry this thing for you, Bob. So when you come up here, it's not too wet. So I don't know if there's time for questions or.
Yeah, thank you. Thank you very much. Great presentation. We have a few minutes for questions.
I'm very curious to know if you've had a chance to look at how the structure of the breeding program has changed on a genetics level. Like, right, so like one of the known problems with genomic selection is, yes, right, like now you got a bunch of stuff that has low beta glucan, but now it's all like highly related to each other because they all like came from one lineage. I mean, like, have you looked into any of that? I mean, even just like anecdotally in terms of pedigrees and stuff like that.
Yes, yes. It's always been the case with malt barley. That's always been all of our other breeder friends and other crops always go, you people just do nothing but cross sister lines, right? And the genetic in breeding, you don't think about it that way, but that's what they are. They're so they're lined from the same cross. And I had a slide from my New Zealand nursery, and it was of 6 rows again, and you would have seen all these uniform rows, and they were F3s. And so, yes, it does push things. You got to be careful. You got to make sure that you are keeping variability in the program. It's harder. It's something you have to concentrate on more. Yeah. And we also do, when we pick parents, we're also looking at structure to make sure that we're not crossing same by same. Yeah. Thanks for that question. Kevin, then we'll go ahead.
Hi, Rich. I have a question about your SNP marker assay for predictions. So as I understand it, you are actually targeting, you're selecting SNPs for specific traits.
Correct.
So, and the way I've seen most people use genomic selection is they just develop a set of markers to create a relationship matrix, and they use that same set of markers to predict all the various traits. So
yeah, I do. I mean, I still use my prediction formula uses all 3,600 markers.
Okay.
But there's still markers on there that may be, and then the variance is going to go to 0 and they're not going to be used anyways. So.
Okay, so you're not just taking like 100 markers to make predictions. You're using the whole set.
I'm using the whole set.
Selected set. Great.
But when I build the array, I make sure there's the best 50 are on there for that trait.
Gotcha. Thanks.
I think Eric had a question.
Maybe a little naive, but is there an asymptote to get to beta glucan? I mean, how low do you want to go? And is there
SCRE right in front of you?
Is there like a negative consequence? I mean, like we always think more is better. In this case, less is better. But and I'm assuming that the beta glucan test is a calcifluor test after it's been malted, and that measures a certain size beta glucan, and there's other size beta glucans that can't be measured in that assay. So, are there issues with filtration that aren't predicted by those low beta glucan numbers? And I mean, there's a whole bunch of questions in there.
No, that's a really good question. So beta glucans, what we hear as breeders, go for it. Go low, go low, go low, right? And forever in the 80s and 90s, we were told for enzymes, especially on the 6-row barleys, go for it. There is no top. As much alpha amylase as you can give us, as much DP as you can give us. But then we ran into problems. Those high alpha amylase lines, they sprout if they get just heavy dews on them. So yeah, there can be big issues. When this variety standard came out, it had really high it had really high extract, but it had high S over T. So no one knew how to use it. But now that's the desired malt type of some companies. So if you go too far, it's yeah, but eventually if it's really worthwhile to them, they'll find a way to use it and it will become the standard. Does that make sense, Yard? Kind of? Yeah.
All right, we have time for one more. Anybody's got one?
Well, thank you so much.
Thank you, Rich.